In this video, I want to show you again the development of different atomic models, starting from the very first one that we know of. Although we have already discussed most of these models in the past, I have two reasons to repeat them. First of all, I would like to demonstrate that it's difficult to say that a model is wrong, because it's due to the nature of a model itself. A model is only a simplified image of reality, and that means that you can, for example, use a very simple atomic model for certain purposes. If you would like to explain heat, for example, it's absolutely enough to consider an atom as a small sphere. Just a very, very basic, simple model. This is totally enough. So you don't need a quantum mechanic model of the atom to explain that. It is way beyond what we require for such a question. So a model serves a purpose. It should explain certain phenomena and also make an atom, for example, visible. And visible means, in that case, that you can imagine what an atom looks like. And now, by looking at historical models of the atom again, I would like to demonstrate that they mostly build up on each other. And so a new model normally is the development of an older model, and this is also the case in new models that we will get to know in this video. And maybe at the end I can also give an outlook on what is still to come, because quantum physics opened a complete new view on physics in general, so that there are certain, you can't just say that there is like the latest model of the atom. We have different models based on quantum mechanics that serve different purposes. For example, in chemistry, I'm sure you've heard about the orbital model, and with the Schrödinger equation in physics that we will slightly touch maybe. We have different models, and still, as you can see, and that's where I want to start now, with Democritus, who was over 2,000 years ago. He just developed his model by a simple thought that if you divide a piece of wood, for example, in two pieces, and then throw one away and do the same thing with the piece that's left over, how many times can you do that? And maybe you also see what he did, that this can be described with a mathematical sequence, like you end up, or you start with 1, and then you have half and a quarter and 1/8 and so on. In maths, you would, well, it never comes to an end, but if it goes along to infinity, you will eventually end up at 0. And he said this can't be the case if you take the piece of wood. So there should be something like a smallest particle. And Dalton came, well, much later, although the ancient Greeks already knew that different types of matter have a different density, so that a certain volume of a substance of different substances have different weights. But Dalton just thought that the atoms have different sizes, which is, well, today you would say this is not true. And in fact, it's not, but it does serve as a model. Democritus, I think he mentioned that these atoms could have different weights as well. So that's quite similar. Again, later I think but it was indeed when I looked that up, the Thomson plum pudding model. I think it was only 1911, and I thought it was way earlier than that. But yeah, he observed cathode rays and found out that a cathode can emit charged particles that we today know as electrons. He found out because they were deflected in a magnetic field, and the Lorentz force was already known. So he had the idea that these negatively charged particles come from the atom itself. So since he didn't have a chance to look inside an atom, but he said the negatively charged particles are coming out, so they were like something like the raisins in this pudding, and the whole mass is positively charged. So that was a correct idea, and although this model is probably a bit out of date today, in contradiction to Dalton, for example, and or even Democritus, that can be used, but the Thomson model is probably a bit useless here, and it's like a semi-state model, because already 2 years afterwards Rutherford did some experiments with the gold foil, which he targeted with alpha particles. And as you can see here in the picture, most of the alpha particles just went through this gold foil of 6 layers, so very, very thin. But he concluded that most parts of the atom must be empty, since so many of these alpha particles just went through and hit the detector with no deflection at all. But some of them, like this one here, they bounced back and were kind of even reflected in a complete different direction, and others was the trajectory was slightly bent. So he concluded that there must be a central mass inside the atom, which we know as the nucleus. And since this is a further development of the Thomson model, it was clear also, because the alpha particles are positively charged, that the nucleus must contain the positive charges, and the electrons, well, are just located in the atomic shell. But this already leads to the question, how can the electrons that are negatively charged well, how do they behave, how do they exist at all in the atomic shell? Because they should be attracted by the nucleus. So if they have no velocity, the atom would be unstable, as you can see here with this arrow. So they would bump into the nucleus and, well, make something like the Thomson model, where we now know this is not how the atom looks like. So still, well, the idea was that they have a certain velocity, so they can circle around the nucleus. And if we compare this idea with gravity, where the moon, for example, circles around the Earth and the Earth around the sun, and this has been going on for millions of years, this thought is not too far away, but we already know that accelerated electric charges emit energy in form of electromagnetic radiation. And we also know that on a circular path, the particle is always accelerated because it changes its direction. So by all means of classical physics, this extended model does not work. However, we reach a new area of physics where we are in 1913, and already 7 years ago Einstein explained the photoelectric effect, and Compton effect was already known. So it wasn't a big surprise and something completely new that the classical physics does not work in the way anymore that the scientists were used to. So now Bohr came round the corner, and he had the idea of a new atomic model that could explain at least certain phenomena like the photoelectric effect and the absorbed spectra of gas that we've already been looking at. So I'm sorry, this is still written in German, so I have to look what a postulat is in English. Now my cell phone is okay. Here we go. Okay. Well, let's just, I will correct that later, otherwise I have to start the video again. But it is like a hypothesis that cannot be proved, like an axiom in maths, which turns out not to be true, but still this works to describe certain observations. It is accepted and valid to use. So we have here the first one states that that electrons circle around the nucleus in an atom without emitting radiation, and that its orbital angular momentum has certain values. Now, we already know the momentum, which is mass times velocity. However, on a circular path, we have a certain problem that the momentum still has to be conserved, so it can't get lost. But if you remember, maybe, I think you were at our Christmas lecture. Remember the following. You're sitting on one of these chairs that can spin around, and you've got your arms stretched out, maybe even with some weight in your hands. And then you start spinning, and you take your arms or your hands closer to your body and the center of mass. And this will increase the velocity or the angular speed. And for the momentum to be conserved, when the velocity gets higher and the radius decreases at the same time, that explains this formula here, as you can see, that the angular momentum remains constant. Yes, so with an increasing radius, you get a decreasing speed, and the other way around. So Niels Bohr, now he said that in an atom, this angular momentum has values or the multiples of h over 2 pi. We've seen this factor before, I think in Heisenberg's uncertainty equations. As you can see here on the left side, n is a quantum number, and it determines the order of the circular path here of the electron. So what can be explained? Well, first of all, what we observed is that the atoms, they absorb or emit radiation with a certain frequency and a certain well-defined energy. So we cannot, or we couldn't explain before why it's not a continuous way, so that only certain frequencies were observed. And Bohr, with Bohr, who said there's only certain orbits, not like for gravity, there could be the moon can be here, but there can be other satellites here and there and there and there. So we've got a continuous distribution of, let's say, energies. But this is not the case inside an atom. That's what we observed. And this is a trick of Bohr, who says there are only discrete circular paths or orbits where the electrons can stay, or where they can be. And with the transition of an electron from one to another orbit, and this is according to gravity in classical physics, we can calculate the energy difference, and this corresponds to h times f. So this is the energy of a photon that is either emitted or absorbed. And as you can imagine, it's only possible for an electron to go from here to there, for example, or the way back. So, and we know that from the photoelectric effect, the energy from a photon is completely transferred to the electron. So only photons with exactly this energy can make the electrons go from here to there, for example, because they can't end up here, because there is no possible orbit. And this is what these two hypotheses of Bohr say. So this is already a big step, although today we know that this is completely wrong. We can still use this model to explain certain things inside the hydrogen atom, which is the simplest atom with just one proton in the nucleus and one electron in the shell. It's a bit like relativistic equations. We know that the equations that we know from Newton are not complete, because when we reach higher velocities, we get into relativistic effects. And so, but still, when we look at the equations of Einstein in his relativistic physics, we see that for very small velocities, the error that we take into account when we use the classical equations from Newton is so small that it's still okay to calculate with it, because it's easier. So it's the same thing here. It's worth looking at Bohr's ideas, and we will now get an insight of what we can calculate with his atomic model. So the idea, still looking at classical physics, is that the energy in one orbit called En is the sum of kinetic energy and potential energy. But this is the same as we know from gravity. So kinetic energy is 1/2 mass of electron times velocity squared. However, we don't know the velocity. Let's look at the potential energy. As we know, this is the Coulomb potential, so it's 1/4πε0 times charge 1 times charge 2 over r in a certain orbit. And we know that we've got one positive and one negative charge, so that makes a minus and then E squared. Okay, because one electron is negative, proton is positive, so in total it's -1 times 1 times, well, the E. In this formula or equation, we don't know the radius of this orbit, so we will need to find another approach. Again, looking at classical physics, on a circular path, we know that the centripetal force, how is it called? Let's say F Z is equal to, and in the case of gravity, it was the gravitational force, but now it's the Coulomb force. So you put in the formulas here. And this equals to E squared for πε0 and now Rn squared. Now here again we have the radius and the velocity that we don't know. But if this cancels out, and let's move the Rn to the left side, so we get Rn MEV squared is equal to this one here. And now we see that the left-hand side, Rmv squared, is quite similar to Bohr's first equation here. So if we look at the orbital angular momentum and we times it with v, that would then we would end up with a v squared, which is exactly what we've got here on the left hand side. So this corresponds to Ln times v n, and all right. And now we look at Bohr again. Let me take a different color. In his first hypothesis on the right side, he says the L is equal to n, so the order of the orbit, and quantum number, the main one, times h over 2 pi. So L and if we want to have an expression for Vn, we divide by ln or we times by 1 over ln, which is in this case 2 pi over n times h. And if we do that, we see that we have 2 pi times e squared over 4 pi epsilon 0, and then let me just h and change the order here. So the 2 pi cancel out, so we end up with e squared over 2 epsilon 0 h times 1 over n. For the velocity of the electron in a certain orbit around the proton in a hydrogen atom. So now I think if we, how can we get the radius? Let me just have a look. Okay, so we go back here. We insert the velocity and we get h squared epsilon 0 pi me e squared times n squared for the radius. Now we see that all of this are constants, so we can calculate the value, and well, if we put in 1 for n, we achieve that the radius is 4.29 times 10 to the power of minus 11 meters, and this is roughly 0.5 times, or let's say the diameter is, then we double the value, and this is around 10 times 10 to the power of minus 10 meters, and this is called 1 angstrom. We have seen that before in the last mission. This is a unit that was put into place because 1 angstrom corresponds to the diameter of an hydrogen atom, and I've been looking at, just Google the diameter or the radius of hydrogen atoms, and I still only find the result of Bohr, the Bohr radius. So that tells me that this is still used, and I mean, the problem nowadays is that we know this is not correct. So there is no, well, we know that in quantum mechanics, basically everything is determined by probabilities. So we know that the radius can't have a fixed value. So it's mainly we have a certain probability for the electron to be here or there, even inside the nucleus, which is, from the classical point of view, totally crazy. But nevertheless, that means that we can't really say the radius is this or that. So the electron can also be here, although it's less likely than at a smaller distance to the nucleus. But still, as I said, the value of Bohr is simply just very good. So it is still used, and that's why this Angström is still used. I mean, it is the diameter will still be around 1 angstrom anyway. So and calculations where we use the Bohr radius they just give good results. I can remember that from my studies at university. So as I was saying before, some people question that we still look at Bohr's atomic model, although it is proven to be wrong. But still, it plays a major role in the development of modern physics. It gives us, for certain situations, correct results, or at least results that are good enough for us to work with. And historically, it was the first step, the first model that combined the classical physics with the modern physics, quantum physics. And as we will see when we look at another model, that we also take certain aspects from classical physics to explain, for example, why or how electrons can be seen in the nucleus and in the atom. But well, that's still we will discuss that a little bit later when we point out the limits of this model from Bohr.